that for the linear equation for second law, it's going to turn into torque is equal to I alpha. And there is a proof of that. We understand that in all these transformation equations, you just replace the variables and it works. For the type of problem that we're going to see, it's the process is very much like coupled motion, because our pulleys now have mass. So prior to this, all of our pulleys were massless. So if we have a string wrapped around a pulley and then a mass attached to it, so this string is kind of wrapped around there, kind of like a yo-yo would be. And we released that mass. Now, if that was just a frictionless, massless pulley, that block should accelerate at the rate of gravity, all right, because there's nothing resisting it, okay? But now that it has mass, we have a resistance force. So there is going to be a tension up on that block and mg pulling it down. But now on this pulley, since this is now an object that has mass, the tension is going to be pulling at that location on the pulley, all right? And that pulley is going to rotate around its center. So that torque, that creates a torque around that center point. So in coupled motion, we had to draw our free body diagram for each object. We had to write our sum of all force equation for each object, and then combine them to only get one variable. What was usually the first variable we would be able to solve for in coupled motion? It was always the acceleration, then plug the acceleration back in, and that was about 90% of the problems. It's kind of similar for this as well. So we have our free body diagrams drawn. So if we sum up our forces in the linear direction, we're going to have, I'm going to make downward positive. So I'll have mg minus the tension, and that is only going to cause the little mass, little m, to accelerate. Say it again? That's little m. Do you want me to call it 1 and 2? 1, 2. All right, so there's our sum of all force equation in the linear direction. In the rotational direction, we have sum of all torques. We have one force creating a torque. It is the tension. All right, so it's tension times the radial distance away. That's the only torque acting on that pulley, and that is going to equal to I alpha. So what values we probably will not know are going to be the tension, the linear acceleration, and the angular acceleration. So these would usually be the unknowns. So let's combine what we have and solve for unknown. Again, usually you want to solve for the linear acceleration first. We know in the angular direction that the linear acceleration is related to the angular acceleration through this equation. So we're going to substitute this into the angular equation to relate the angular motion to the tangential acceleration, which is the linear acceleration of the block. So the rate at which that outer edge is accelerating tangentially on the pulley is going to be equal to the angular acceleration, assuming that the string does not slip over the pulley. And for a pulley, we have to utilize that the I is a solid disk. If we do not know that, we look it up. All right, so for a solid cylinder about its central axis, which is this one right here. All right, 1/2 mr squared. So again, if you don't know it, look it up in the book, or you can, the common ones are the hoop, the cylinder, and the sphere, and the rod. All right, every once in a while you'll have to use one of the oblong weird shapes, but most of the problems on the AP exam utilize a hoop, a sphere, a hollow sphere, or a cylinder. Okay, so the eye of that cylinder is going to be 1/2 m2 r squared and we have a lot of stuff cancel out now. So this r cancels one of those. This r cancels the other r. So we're left with the tension is equal to 1/2 m2 times A. So now that we know the tension in terms of the acceleration, we're going to plug that into this equation. So again, like coupled motion, we're solving for the linear acceleration first. We got rid of the unknown tension. We should know the mass and radius of the pulley and the mass of the block, again, as a generic solution. There are little instances where they will ask you to solve for other things, but the process really doesn't change except for what are you solving for and substituting into the other equation. So here we have to just manipulate to get the mass or the acceleration by itself. Pull out the acceleration. Now on the AP test solutions, they almost never have this fraction in that solution. So what they'll do is try to get that fraction out of that parenthesis, and to do that they have to multiply everything by 2. So we're going to multiply this by 2. We're going to multiply this entire side by 2, which will distribute in here. So that 1/2 kind of will cancel out. So that the final answer for the acceleration here would equal 2 m1g all over 2 m1 plus m2. Yes?
Will the radiuses always cancel out?
That is a trend, yeah. Okay. I don't like always statements. That's a safe one to kind of assume is going to happen, all right?
So if we have like the question that's on the test, then we probably won't be given the radius.
Right, yeah. Or a problem like this, it'll more ask like, this would be part A. So this is your answer for part A on the exam. Then probably the next question will be, what is the tension in the string? Do we want to continue, or is this kind of enough to understand where to go? You know that you then have to substitute this into one of your starting equations. There's one that's easier than another. I would plug this back into this equation. All right, and then you will end up with what the tension is equal to. Then probably the next one would be what is the angular acceleration, or that would be part B. And then again, you can plug this right into this equation. And then again, there'll be little algebra differences if they are asking you to solve for something, bless you, different. Maybe we don't know the mass of the pulley. Right? So we would have to know, they'll always give you problems that you can solve. All right? You'll always have enough information, and you just have to do the different algebra. But the setup is the same. Draw the free body diagram for each object, sum up the rotational forces, sum up the linear forces, combine those equations in that way, and you'll be fine. All right, there's only 2 problems on this WebAssign. However, this is an important type of problem that you're going to have to solve, on the AP test. Okay. On the next chapter, we start rolling, which again uses a similar process. So instead of things just spinning, they're going to be moving linearly and rotationally. So here it's just rotation.